Live from the BBC, The Naked Scientists.
This week, we're looking into the science of the weather forecast, or to give it its proper name, meteorology. How are weather forecasts predicted? How accurate are they? And also, we'll be hearing from researchers that have now built mathematical models of how we build up weather and climate, and how they can look into the future, not just months, but years ahead, to see what the weather has in store for us. That's coming up tonight, and if you'd like to join in the discussion, call me now. I'm Chris Smith, 08459 25 2000, or you can email chris@nakedscientist.com. Also here to help present tonight's programme is Dr. Cat. Hello, Cat.
Hello. We're going to be bringing you news tonight of the fisher-pod, the missing link between creatures that lived in the sea and creatures that lived on the land. Chris has been finding out about that. I've been looking into snoring and who's more likely to snore than other people. And unfortunately, we don't know whether we can stop that yet. And also bringing you news of an exciting writing competition for all you aspiring science writers and broadcasters out there.
And we also have up for grabs a trip round the Met Office, because one of our guests this evening is Alex Hill from the Met Office. That's where they forecast the weather. We'll be talking to him later, but if you win our competition this evening, then you could be off down there to join Alex, and you could put together your very own weather forecast as you hear on the radio. So get calling now, 08459 25 2000, or email chris@nakedscientist.com. Anything to do with the weather, or if you have any general science questions, get them in now, and we'll try and squeeze them into the first half of the programme.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
That's a listener to another radio station.
Is that familiar? A familiar sound, it certainly is to me. Good grief. Snoring. Snoring is a problem, but scientists in Cincinnati have been studying snoring to work out if you can predict who is more likely to snore. And they found that if your parents snore, their children are more likely to snore too. And also children who have allergies as well are twice as likely to snore as children without allergies. And the researchers studied over 600 children who were about 12 months old. Usually when people do snoring studies, it's on slightly older children. This is the first study of babies who are the children of snorers. And they found, that if your parents snore, then your children are more likely to snore as well.
Any clues as to why that might be? For instance, are the kiddies who snore like their parents very, very large, or something like that?
I think it probably is that. So people who are overweight are more likely to snore. It's to do with your palate. And also allergies can make people snuffly, their noses get blocked up. So allergies do tend to run in families as well. So maybe that's it. The researchers are going to follow these children, being from 1 year old to about 5 years old, and see if they can work out more links.
Now, here's an interesting question. Kat, being a woman, you can help me out with this. What does a girl look for in a man?
A big wallet and large trousers.
Well, yes, if you were filling in the survey that Fiona Moore from the University of St Andrews put together recently, about 20 years ago, that would have been true. But they've surveyed 1,851 women between the ages of 18 and 35, and they found actually that what women look for in a man these days has changed quite dramatically. Because historically, yes, you're quite right, women used to report overwhelmingly they go for the size of the man's wallet. But now, they've totally changed. And what women rate above all else now, and we can ask Emily Shuckburgh, who's one of our guests this evening. Emily, what do you rate above all else when you're looking at a man's qualities?
Well, the classic things are good sense of humour and...
GSOH, good standard of hygiene. Quite right.
That too.
But what they've found in their survey is actually it's now attractiveness. Women are now going overwhelmingly for men that actually look nice, unless the women are really hard up. And this is really interesting. What they've found is there is a strong relationship between how financially independent a woman is and the kind of choice of man she picks. And if a woman has more financial independence, i.e. she's got a good wage coming in, she doesn't need to rely on a man having a big wallet, so she can choose she's better able to choose what kind of bloke she wants to go for. Whereas women that are harder up in their survey still went for men that were richer, on average.
I still think it's all about personality. So bad luck, Chris.
Well, anyway, we're talking about the weather this evening, and if you'd like to join in our discussion later, 08459 25 2000 is the phone number, or you can email me, chris@nakedscientist.com. On the subject of the weather and the climate and things, here's something we all pray for, a nice, clear blue sky. And Derek, who is our kitchen science guru, is out at Downham Market High School this evening. He's joined by Sheena Elliott, who's an engineer and a PhD student at Cambridge University, and she's got two volunteers with her, Matt and Sarah. Hi, Derek.
Hello there, and welcome this week to Downham Market High School. We've come here this week to the Science Lab to do some experiments, and with me is a new recruit to the Naked Scientist who's going to be doing a few of these kitchen science features for us. So could you introduce yourself and tell us what you do, please?
Yeah, my name's Sheena Elliott, and I'm a PhD student studying physics at University of Cambridge.
Excellent, thank you. So what is it then we're going to be doing this week?
Today we're going to try and do some blue sky experiments. We're actually going to be trying to simulate blue sky in the lab.
OK, looking at blue sky, there we go. And we've also got a couple of volunteers here who very kindly come down to help us do it. So, guys, could you tell me your names and what year you're in here, please?
Hi, I'm Matt, I'm in Year 10.
I'm Sarah and I'm in Year 10.
Thanks, guys. OK, and I've got to find out whether you're into science, because obviously we're out here kind of promoting science a bit. So, Matt, do you like science?
Yeah, but it's all right.
OK, and yourself, Sarah?
Not really.
OK, so are you open to us persuading you it's actually really cool and fun?
You could try.
All right then, well, we will be trying to persuade you that science is indeed very, very cool. And so you at home, of course, you can do this experiment as well. It's very, very easy. And so the things you need at home are, firstly, some kind of vase, a transparent kind of tall container. So a vase would be great, for example. Also kind of a tall glass would be OK. Also, you need a bit of milk. And you need a torch, and that's basically it. So Sheena is now going to tell us exactly what we do with all these things.
OK, so first of all, we just need to fill the vase or our tall glass container to the top with water. We then just need to put in a few drops of milk, and we only really need a very little amount of milk to put into it. Remember, if you put milk in, you can't take it out, so just add a little bit at a time until we get the effect that we want.
OK then, well, Matt and Sarah are here ready to help us do some preparations for the experiment, and we've already got a vase here, but we do also have some milk, and we've actually got the vase filled up with water. So, Sheena, could you instruct them what to do with the milk exactly?
Yeah, all you need to do is just take the milk, I've got a teaspoon here, and just add less than a teaspoon to the vase and stir it in.
OK, so that's really a very small amount of milk, guys. So here we go, then. OK, and Sarah, what does it look like in there?
Cloudy.
OK, and so is that mixed well enough, or does it need to be more mixed?
You might just need to stir it around a little bit more so it's the same colour all the way through.
Yeah, because it's kind of quite cloudy at the surface at the moment, so Sarah's just kind of stirring it all the way around. And I think that's OK, is it? Yeah, OK then. So there we go, we've got some milk in the vase. What next?
Now we're going to turn the lights out in the room and then just take the torch and shine it in through the side and just sort of observe the colours that we see in the vase.
OK then, and what kind of different things, what different angles can you shine the torch from?
So I think if we start by shining the torch in from the side and then looking at right angles to the beam, so we won't be looking directly into the beam, we'll shine it to the side and we'll look at right angles. And then secondly, if we then look through the vase, so actually look directly into the beam with the vase in the way of the beam. And then finally, if we shine the torch from below the vase and look from above and see what that looks like from above.
OK, so there you go. You heard it there from Sheena. You've got to shine the torch into that slightly cloudy vase with the water and the bit of milk in it from a few different angles, from the side, look at it from right angles to the beam. You can actually shine it from the bottom upwards and see what you get when you look into the beam. Lots of things for you to do there. And, of course, we will be doing that later here at Downham Market High School. And, of course, Matt and Sarah are ready to do it. So, Matt, what do you think is going to happen?
Hopefully the effect we're looking for.
Well, indeed, yes. No more precise than that. Well, that's fair enough. Sarah, any idea?
No, I don't have a clue.
OK, well, all sorts of answers there. OK, well, we will certainly be finding out exactly what happens later on. And, of course, you at home, you don't have to wait until later in the show because you can do this right now if you've got these things at home. You can give us a call and tell us the result. And if you can do so, then you can win a prize from us, the Naked Scientists. So the number you need to call is 08459 25 2000. And you can also email, if you like, chris@thenakedscientist.com. And so if you can tell us what happens when you've got that water in the vase with a bit of milk in it, shining a torch through and looking at it from various angles, tell us what happens and you can win that prize. So there we go. We'll be back at Downham Market High School later on in the show to tell you what happens and explain how it all relates to things you see around you. Until then, it's goodbye.
Thank you very much to Derek, Sheena, Matt and Sarah. We will be rejoining them in roughly 50 minutes or so to find out the answer. But if you think you know the answer, you could win yourself a trip down to London, courtesy of the Naked Scientists and Alex Hill from the Met Office. Sounds like a kind of betting agency or something. That's William Hill, of course. But yes, you could win yourself a trip down to London, and you get to work out your own news weather bulletin, courtesy of Alex's help. But he'll show you exactly how the Met produces weather forecasts, and we're going to be talking about that later. So if you have any questions for us, 08459 0859 25 2000, or email me, chris@nakedscientist.com. Got a quick email here from Siobhan Braybook, and she's in University of California, Davis, and she says, "Hello, Naked Scientists. I'm a graduate student in plant molecular biology at the University of California, Davis. My whole lab listens to your podcast, and we have some lively competitions to do when it comes to answering the quizzes. Thanks for expanding our science beyond our little green friends. Keep it up. We love you guys," from Siobhan. So thank you very much for that. That's fantastic. If you have an email you'd like to send us, get your name on the show, just email me, chris@nakedscientist.com.
And we've had a couple more emails here. Another PhD student. You PhD students, you love us. From Canberra in Australia. This is from Kate Kearney, who's a PhD student studying the cell biology and genetics of Drosophila prostate glands. She says she listens to our podcast in the fly room while she's dissecting her prostate glands out. And also from Bob Perk, who says he loves listening to our show on podcasts. It's great to hear rational thought on the media, unlike the drivel that we normally get. And he wants to know, is Kat really as hot as I imagine her to be? And I'm afraid no, I'm 37 degrees like everyone else.
There you are. Now, we're winding our watches back 380 million years now to a time when the first animals began to substitute feet for fins and heave themselves out of the sea and onto land, because, believe it or not, we all come from the sea. We all evolved there. The complicated animals that became early humans and now subsequently humans all came out of the sea at some point. Now, we know that must have happened. Fossils from animals undergoing this transition, though, are really hard to come by, and that's what makes this week's discovery really so important. Neil Shubin from the University of Chicago and his colleagues have uncovered Tiktaalik, and this is a fish which has got all of the features of a primitive wrist and elbow in some of its fins, and it has very bizarre features. It's got a head rather like a crocodile with nostrils on the side and eyes on the top of its head and ribs. Neil told me earlier why his finds are so important.
The transition from a fish that lives in water to an animal that's able to live on land is one of the great transitions in the history of life. We know from a variety of different lines of evidence that this transition happened around 380 to 365 million years ago. We also know the likely players involved, the different kinds of fish that are likely to have given rise to land-living animals. Now, remember, when we're talking about land-living animals, we're talking about a whole branch of the tree of life, the branch that includes amphibians, reptiles, birds, mammals, even us. So this is really a part of our own, albeit very ancient, evolutionary past. The discovery is really important because it's the discovery of a new kind of fish that blurs the distinction between fish and land-living animal. It has a mosaic of features seen in both. Like a fish, it has scales and fins and a very primitive jaw. But like a land-living animal, it has ribs that fit together. It has a neck where the head can move around separately. It has a flat head like primitive amphibians. And importantly, when you look inside the fin, it has a number of bones that compare very closely to the bones in our own wrist, in our own hand. And so in that sense, it's a real mosaic and tells us, to a great extent, how parts of our skeleton evolved.
And where was it found?
We found it in a place called Ellesmere Island, which is one of the northernmost islands in Arctic Canada, several hundred miles south of the North Pole. When we work there in the summers, it's daylight 24 hours a day. There are polar bears walking around. There are muskox. It's a classic Arctic landscape with ice and glaciers. But between the ice and glaciers is bedrock. And that bedrock is Devonian age rock of about 375 million years old. And the environments that are contained in those rocks reveal an ancient river or delta ecosystem. And within that delta ecosystem, we're finding a variety of different kinds of fish, of which this new kind is just one.
But a common criticism in the past has been that there are hardly any of these fossils ever found, these transitions from one state to another.
Yeah, exactly. And this really puts a lid on that, because not only do we have a beautiful transitional form, but we have multiple skeletons of it. And when you compare this creature, the new one, to other creatures which we've known about before, a creature called Panderichthys or Elpistostega, which are creatures that are known from the Baltics or Russia. Compare them to the earliest known land-living animals, a creature known as Acanthostega. When you put this whole series together, it's truly one of the remarkable transitional series between different kinds of life in the history of the Earth.
How do you think it came by these really interesting adaptations in the first place, though?
Let's think about how this thing lived. What it has is a flat head with eyes on top, much like a crocodile. It has nostrils on the side. It's a very flat animal. It has an appendage or a fin that's able to bend its elbow and its wrist. It has a rib cage which suggests that it was able to support itself in gravity. What you have is an animal that's clearly specializing for life on the water bottom, in the shallows, or even out in the air for periods of time. So if we look at the geology of the site this thing came from, it came from a very small stream in a large delta environment, a giant swampy environment. And it's within these small streams which we believe that we find the locus for the evolution of many creatures that later forms used to walk on land.
So now you know who to blame when you next get tennis elbow. That was Neil Shubin from the University of Chicago introducing Tiktaalik, the first fish to find its feet.
The Naked Scientists, supported by the Wellcome Trust.
I don't know who remembers, but a few weeks ago we had Julie from Cancer Research UK on the show to tell us about a competition that the charity is running. And there's still enough time to enter. So if you're based in the UK and you're between 11 and 18 and you want to be a science writer or broadcaster like me and Chris, which is so much fun, you should enter this because it's a great opportunity. The competition's called Science of Tomorrow. And all you have to do is imagine what is science going to be like in 2056. Will there be no scientists? Will it all be robots? Will we have bird flu or a more mysterious sort of illness ravaging our population? You need to write 700 words. There's different prizes that you can win for the different age groups, 11 to 14, 15 to 18, and regional prizes too. Competition's being judged by all sorts of people, including Zoe Salmon, the Blue Peter presenter, whoever she is. God, I feel old. And loads of prizes, including a trip to the Science Museum up for grabs. So 700 words on the Science of Tomorrow, and get entering on www.scienceoftomorrow.org.uk. And so that's Cancer Research UK's new competition. There must be someone out there who's got the talent. We want to find it.
It's Chris and Kat, the Naked Scientists, and if you have any questions for us science-wise, just email them in, chris@nakedscientist.com, or you can phone us live. It's 08459 25 2000. Got an email here from the States. It's from Alison Marcus, who's listening somewhere in America, and she says, what's the smallest number? We can't decide whether 0 is smaller or larger than minus infinity. Yours, hopefully, from the Marcus family. So what does everyone out there think? Is 0 larger or smaller than minus infinity? A very challenging question. I'm not sure I know the answer to that one.
I think that's one for the pub. Should discuss it after a few beers. Anyway, we're going to go stateside now, over to the US, and speak to Chelsea Wald and Bob Hershen from the AAAS. And we have their science update for this week. We're going to find out how genetically modified crops are being used and how obese people are more susceptible to pain.
For the Naked Scientists this week, we'll be talking about a group of scientists trying to alleviate poverty in the developing world. But first, obese people face a heightened risk for all kinds of other conditions like diabetes, heart disease, and stroke. Now, new research suggests they may also be more susceptible to pain.
Exactly, but you might not know it from asking them. This according to Ohio State University psychologist Charles Emery. He and his colleagues found that compared with non-obese people, obese people's bodies were unusually sensitive to a pain reflex test. The finding dovetails with other research that links obesity to inflammation.
So you see higher levels of C-reactive proteins that we know are associated with inflammation in obese individuals. And those inflammatory factors are also found in people with chronic pain. And so it makes a good deal of sense that, in fact, people who are obese and have this chronic inflammation could be at greater risk for pain.
Yet in Emery's study, the obese people didn't report feeling any more pain than anyone else. It's not yet clear if they actually experience pain differently or were just being stoic.
Over the 20th century, the productivity of that American food staple, corn, increased more than 1,000 times. That's thanks to science. But other crops have been left behind, along with the people who rely on them.
And one crop in particular is cassava, also known as manioc. It feeds some 700 million people in the poorest countries, but it's susceptible to viruses, insects, and drought. That leaves cassava farmers with hardly enough to feed their families, much less any excess to sell. That's according to plant biologist Claude Fouquet of the Donald Danforth Plant Sciences Center in St. Louis, Missouri. He's a leader in an international coalition of scientists working on the cassava plant.
So it boils down to the fact that if the plant itself is not capable to produce enough calories per unit of space and family, then these people cannot get out of poverty. So we estimate that if we could double the current world average productivity, which is about 10 tons per hectare, if we could turn this into 20 tons per hectare, then these people could get out of this poverty cycle and could start to participate to the local economy.
They hope to do this by genetically modifying the plant for resistance to drought, viruses, and pests, and to express healthy vitamins and proteins. But they caution that current investment in cassava research is only 1% of what they need to reach their goal.
Well, that's all for this week's Science Update. Next time, along with the Naked Scientists, we'll be talking about marine science. Until then, I'm Chelsea Wald.
And I'm Bob Hirschon for AAAS, the Science Society. Back to you, Naked Scientists.
So if you want to hear more news from Bob and Chelsea, then go and have a listen to their website. It's www.scienceupdate.com. They got loads more stuff on there. Chris?
Got a quick email here from Alice Hudson, who says, "Hi, I'm Alice, 14, from Kent. I've been wondering about this question for a while, and when my brother introduced me to your show yesterday on the way back from Wales, I became addicted to it and listened to over 3 programmes. Then it clicked that you could answer my question for me. So here we go, Kat. You see if you can have a go at this. Why do bubbles of gas form on the sides of a bath or glass while or after you have run the water?" Thank you very much, Alice. What do you think?
I think it's to do with nucleation sites.
What do our guests this evening, Emily Shuckburgh and Alex Hill, think? You agree?
Bubbles, when you look into... The best way of actually describing this, if you're someone like me, is to buy yourself a glass of beer and look at where the bubbles form in a glass of beer. And they always form on the edges, always form on the surface of the glass. And it's exactly the same way as a raindrop forms, and it's exactly the same way as a bubble of air forms. You need to have something for it to form on. And the bubbles usually start on little peaks and troughs on the tops of the glass.
Yeah, I'd go along with that. Sorry.
Avid listeners of The Naked Scientist will have, a few weeks ago, heard Professor Herbert Hubbard doing an experiment where he put some sugar into a bottle of lemonade, and lots of nucleation sites were formed, and the bottle of lemonade exploded. So we've seen it before on The Naked Scientist.
So in other words, let's just summarise for Alice. A nucleation site is a rough area on a surface. If there is gas of any kind dissolved in a liquid, and if you look at water, the reason fish can breathe underwater is because the water's full of oxygen and other gases. It's got those things dissolved in it. So if you have a sharp area, a rough patch on the side of something, that can act as a point where the gas molecules come together and they coalesce or join together to form a bigger and bigger and bigger bubble. And you can see this if you pour yourself a glass of tap water, leave it by the bed overnight, you'll wake up in the morning and it's all bubbly. And those bubbles are formed wherever there's a rough patch on the side of the glass. Tis The Naked Scientists, Chris and Kat, and if you have any science questions like that for us, 08459 25 2000, or email chris@nakedscientist.com. Very, very shortly we're going to be talking about the science of weather forecasting with our 2 guys, Alex Hill with Emily Shuckburgh, and joining us down the line, Tim Palmer, to talk about the prediction of climate and that kind of thing. If you'd like to join the discussion, call us up now.
Sorting out the sparks from the quarks. The Naked Scientists.
Now, over the past few weeks, Daniel Skooker from the European Space Agency has been keeping us up to date on something called the Venus Express mission. And this is the European Space Agency's mission to go and investigate our near neighbour, Venus, the green planet with a runaway greenhouse effect. We're hoping that it can teach us a bit about what happens when a greenhouse effect goes out of control, and also to explore the interesting plate tectonics that they see on Venus, because people are interested to know, are there active volcanoes there on Venus? Now, Tuesday, April the 11th, is a critical time for this mission because the spacecraft has got all the way to Venus, but now it's got to try and get into orbit. And if anything goes wrong, we could be looking at quite a serious cost to the ESA, the European Space Agency. Have put a lot of money into this. They can't really afford for this to go wrong. Here's Daniel.
Later this week, on Tuesday, April 11th, the European Space Agency's Venus Express begins its critical orbit insertion maneuver designed to brake the spacecraft and lower it neatly into a 24-hour elliptical orbit around the hothouse planet. While it sounds easy, it's actually a challenging and fraught maneuver. The focus of activity that day will be the Main Control Room, or MCR, at ESOC, ESA's Space Operations Center in Germany. During a recent live training session, I met Mike McKay in the MCR. Mike is a veteran ESA flight director who has spent many hours on console in this room.
On the large screens in front of us, we can see data such as the ground station status, where we are actually picking up the spacecraft at what time. Critical events will be displayed so that all of the team members are focused on the critical schedule of events that must occur for successful Venus insertion.
Mike says the large, well-equipped main control room enables the flight controllers to work as a focused team during critical events like launch or orbit entry and gives them the central facilities they need to communicate with support teams worldwide. I asked him to describe some of the high-tech drama that takes place here when multi-million euro missions are launched or maneuvered deep in space.
As you can imagine, in a room like this where you have to make the right decision in sometimes seconds to save a mission, the emotions get very high. Flying a spacecraft to another planet, successfully putting it into orbit at 1 million kilometers distance from the Earth, that is really the high that you get in this room. Naturally, there can also be disappointments where you're preparing a team and training weeks and months in advance to an event like a launch, to find at the last minute, because of something not quite right, we get a delay for maybe days, maybe even weeks and months. And that is hard sometimes to take.
He described what will happen here at 8:19 GMT on the morning of April 11th when Venus Express fires its main engine to be captured into Venus orbit. Mission controllers will monitor the maneuver carefully via an S-band signal sent from the spacecraft.
Tracking that signal through the burn will allow us to see the changes in frequency of that signal that are caused by the spacecraft speeding up. So we can actually monitor indirectly that the burn is taking place, and that is really the critical aspect of the operations for Venus orbit insertion, to see that the main engine has functioned correctly. It will then disappear behind Venus, so we'll have no signal, and that will mean the excitement in here will be very intense to see, after that period of eclipse behind Venus, will it pop out again? Will we get the signal? So I can imagine here the excitement is going to be very, very intense on that day.
On April 11th, ESA will provide up-to-the-minute reports on Venus Express and Europe's arrival at Venus for what is shaping up to be one of the most significant science missions in the agency's history. For more news and information on the World Wide Web, access www.esa.int. For the European Space Agency, I'm Daniel Skuka, reporting from the European Space Operations Center in Darmstadt, Germany.
Good luck to everyone at ESA on Tuesday. I'm sure we'll all be looking out. As long as bird flu doesn't have something to say about the whole issue, we'll be watching there on TV probably.
Stripping down science.
Okay, let's do it.
The Naked Scientists.
We're talking this week about the science of weather prediction and weather forecasting. We'll be finding out very, very shortly how we can build mathematical models of climate to find out what the weather will be doing, not just next month or even next year, but maybe several years into the future. But right now, let's talk to Alex Hill from the London Met Office. Hello, Alex. Thank you for coming in. Tell us just what goes into making a weather forecast.
Information, vast amounts of information, just about sums it up. We have everything from satellites to men to aircraft to everything else to get a description of how the globe is behaving at one particular time. So at the start of the day, for example. And then the great number cruncher in the sky, which we call our Met Office computer, it then integrates over a large numbers of second-order differential equations, if you want the mathematical term for it, for thousands of spots and thousands of feet up in the air. So we essentially describe the atmosphere in a computer.
But what sorts of things are you measuring to do that?
Actually, just two things, principally wind and temperature. And everything else can be derived from that. So you get an idea of wind and temperature, you get an idea of humidity, obviously, from satellite pictures, clouds, that kind of thing. And once that's all in the model, the machine has a, if you like, a kind of description of how it's likely to behave. And then we run that model, and that model runs very, very quickly.
But you're continuously refining this model, presumably,
in order
to get it better and better. Who came up with it?
The first one was actually way back in the early parts of last century. A chap called Richardson and Fry worked on a lot of the basic mathematics of it. They reckoned that we didn't really see the first computer trying to run it until well into the 50s, and that computer, if you ever see a picture of it, was very different from what we see nowadays. It was in fact about the size of a 4-storey house and was filled with valves, and probably had less computing power than your average pocket calculator these days.
So basically you have a model that says this is the readings we have across the country. When we have these readings
across the world, you've got to do it globally. You can't do it just for a small area.
We have these readings, and these readings usually add up to the following happening, and that's going to be our prediction for tomorrow. Is that basically how you do it?
That's a fairly simplistic way of looking at it. Essentially, it's a lot more complicated than that. What the model does is it describes the atmosphere first of all. You have an idea of what the atmosphere is behaving like, and then it breaks it down into blocks. And within those blocks then, and those layers within the upper atmosphere, and indeed down into the depths of the oceans, and how the land behaves, we have that modelled as well into the computer.
Where are you getting all this data from? The temperature and the wind speed, where's that coming into you from? Who's measuring it?
Oh, everyone. It's a totally international operation.
What are they doing? How are they getting that data?
Well, lots of it's just a man going out and measuring the temperature and sending the message in on a teleprinter. Or you get direct readings from satellites, or you get direct readings from aircraft, you get direct readings from ships, you get direct readings from oil rigs. There's lots of different ways of getting the information into the machinery. And we have things like radiosonde balloons that are launched carrying instrument packages up into the top of the atmosphere, and that's a regular occurrence, every 6 hours virtually.
So in terms of predicting wetness and humidity, how can you tell by looking at the clouds how wet they are? Or do you measure humidity as well?
Well, we do measure humidity, yeah, but it's a derived product. It's not a direct measurement in many cases in the computer model. You simply take a parcel of air and cool it, and if you cool it enough, you eventually form a cloud. And that's the start point. That's the basic science of it.
I'm pleased that we've got loads of weather experts. There's something I've always wanted to know ever since I was a kid, seeing mackerel sky, that really distinctive pattern of clouds. What causes it? What does it mean?
I haven't got a slight... Oh, yes, I remember. Mackerel sky. There's lots of these ones. Mackerel sky is just a very chaotic bit. You usually see it after a cold front's gone past, and it's just the remnants of the cold front you're seeing with the sun shining through it.
Because it's beautiful, a sort of really regular pattern of clouds. Thank you.
It can be, in fact,
since I was a kid.
I don't know if you've seen all the fuss recently in the newspapers about cloud watchers.
No.
They go looking for noctiluminescent clouds.
Yeah, they go looking for lots of different clouds nowadays, and it's they want to get rid of blue sky thinking as a phrase.
Can I just ask you one quick question which just popped into my head, which is that I've heard the old explanation for red sky at night, Shepherd's Delight, trotted out, which is that historically, usually, if you've got a front, it moves in one... Well, principally in one country, the weather comes from one direction towards the other, since the sun always rises on one side and sets on the other. Therefore, if you've got clouds going away from you, they're going to be clouds where the sun's setting, and there must be a clear sky where the sun is coming from. So that it would make the clouds look orange when the sun's setting. In the evening, they'll look orange in the morning if the cloud's rising. If the stuff's coming towards you, there's the explanation for red sky at night, Shepherd's Delight, or red sky in the morning, Shepherd's Warning. Is it true?
No.
Where does it come from?
Okay, I say no. I mean, a lot of these things are fun. Let's be fair. And in certain situations, it will work. And we get... If the wind's in the west, then fair enough. When your weather's coming from the west, then fair enough. If you have a red sky night, the chances are it's likely to be a reasonably fair day the following day. If, however, the wind is in the east and you get a red sky night, the chances are you're in for a cold, wet day the next day. So you've got to be careful and get everything mixed up. The other thing, of course, is that they say it's farmers and they say it's shepherds. And I have a good friend who's a sheep farmer in the south of Scotland, and he hates it because it usually means in March, if you get a red sky at night with a westerly wind, it gets very, very cold, which is dangerous for the lambs. So, not all the shepherds would be pleased.
We've had a question in here from Paul Brett in Norwich, and he says, do sunspots affect the weather? So these are different spots on the sun.
Hang on, let's just also have a chat to Richard, because Richard's sort of asking something similar. Hey, Richard.
Hello.
Thanks for joining us on The Naked Scientist. You were also interested in solar activity and the weather.
Well, that's right, yes. I'm on some discussion boards, and we're talking about this right now. And there seem to be two aspects on this. Are there any immediate effects, like when solar bursts occur? And secondly, what about the long-term cycles, like the 11-year cycles? Do they affect things like the jet streams and so on and so forth?
You're in the right place to ask.
What do you think, Alex?
I think you do get a slight impact on it, because you get more energy input. When the sun's particularly active. But it's a fairly routine and regularly forecast cycle, so we wouldn't use it hugely to impact upon a day-to-day weather forecast.
And if you're talking about longer-term weather, if you're starting to talk about climate, then it's certainly the case that if you look at, for example, at the last century, then early in the last century, then periods of strong solar activity were associated with periods of warmer temperatures, but that influence in the later part of the century was vastly outweighed by the effect of increasing levels of carbon dioxide.
Yes, it just seems to me that if there are any effects from the sun, that these effects are very elusive and you can't really sort of directly make a correlation.
What do you think?
I think what we're saying is that when you calculate the amount of energy that comes from the sun, you get a little bit extra when the sunspots are very active. So that does tend to make the weather perhaps a little bit more active. But its actual impact on me as a weather forecaster is relatively small.
Right. Well, what about the science of, or this theory that the jet streams are possibly affected? I think in America they regularly give data on the jet streams high in the ionosphere, but in Britain.
Yeah, well, that'll impact on wind speed, won't it?
It will have an impact in the sense that there's more energy floating around in the atmosphere, which tends to mean that the jet streams are a trifle stronger. But the effect is so small that it's probably not even worth bothering about.
Richard, do you want a quick go at the quiz?
Go on. Why not?
US Pentagon staff get through 1,000 rolls of toilet paper every single day. Is that science fact or science fiction?
I don't know. Ask Bush.
You've got to give me an answer, fact or fiction?
Fiction.
You're quite right, yes. The current estimate is that the Pentagon gets through 665 loo rolls every day, though maybe it does go up whenever George Bush comes up with an idea for Middle Eastern peace.
Me right off.
And next one, Richard. Acetyl salicylic acid is the chemical name for aspirin. Is that science fact or science fiction?
It's true.
You're absolutely right. Dates from the 1860s when the chemist Felix Hoffmann came up with the idea as a more stomach-friendly alternative to willow bark, which is where you get it from.
Thanks, Richard.
OK, bye-bye.
Right, you are listening to The Naked Scientists, Chris and Kat, and if you have a question for us about the weather, 08459 25 2000's our phone number, or you can email me, chris@nakedscientist.com. Right, now we're going to head down to the London Weather Centre itself, because Fran Beckerleg, who's our mobile Naked Science reporter, is finding out about the different instruments that people like Alex Hill, who's here in the studio, use to predict the weather. Hello, Fran.
I'm up on the roof of the Met Office's London Weather Centre. This is one of many hundreds of weather centres across the UK where information is collected to provide short and long-term forecasts. I've got Simon Cardy from the London Weather Centre with me. Simon, there's a lovely view from up here. We're quite high up. I understand this square we're standing on is quite special at Christmas.
Yes, on Christmas Day we were out here looking for any snowflake that could fall on the London Weather Centre roof and let the bookies know if there's a day of snow here at London.
That must be a bit of a chilly job.
It sure is.
So what kind of data is collected up here?
Well, temperatures are the main thing. We've got several thermometers which tell us the maximum temperature and the minimum temperature, and also that helps us work out the humidity of the air as well. It tells us how wet or how dry the air is.
Perhaps you could tell me a bit about some of the instruments that you use here. What's this green bowl-like thing here?
Well, this is going to collect the rain that falls, or the snow or the hail. The rain falls through this green bowl here, and every 0.2 millimetres that falls, we get a little click on the machine downstairs, and that's how it works out the intensity of the rainfall. Now, the rain gauge next to it, we collect rain in here too, and this is measured at 9 o'clock in the morning and 9 o'clock in the evening, and we get 12-hour totals of rainfall.
Perhaps you could tell me a little bit about this white thing over here that looks a little bit like a beehive. What goes on in here?
Well, this is a Stevenson screen. It's made of wood. It's really like wooden louver doors put together, and it's painted white so it reflects some of the sunshine away, because we like to know what the temperature is in the shade, because when the sun gets on the thermometers it can sort of adversely affect the temperature reading. So just opening the door here now, we can see we've got several thermometers inside. One of them is reading the maximum temperature of the day, and we'll read that at 9 o'clock this evening. And the other thermometer reads the minimum temperature of the night time.
So what's the temperature now? Can you tell me?
Yeah, at the moment the temperature's not doing too bad. We've got 13 degrees Celsius, which is 55 Fahrenheit.
Is that a usual kind of temperature for this time of year?
We've had lots of sunshine up until now, and the temperatures have risen quite well, responded well to the sunshine, and in fact that's about average for this time of year.
Fantastic. What happens to the data once it's all been collected?
All the data from hundreds and thousands of weather stations across the UK and across the world gets input into a massive computer model, works out the forecast for the next few days, and in fact the next few weeks or even seasons ahead.
Now, all this equipment looks quite basic. Are there any new technologies being developed to make forecasting more accurate?
Well, we use satellite pictures very regularly now, but we get pictures in every half an hour, and that's a great help to the forecast. We also have radar rainfall, so we can see what type of rain's falling, if it's really heavy or light rain or drizzle. Taking the observations that we've just talked about, using the laws of physics, we can then work out the forecast for the next few days ahead.
Thanks very much, Simon. Back to you in the studio, Chris.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
Now, the next person we're going to have a chat with is someone who works on how to predict the weather ahead of time, and that's Tim Palmer. Hello, Tim.
Hello there, Chris.
Good evening. Thank you for joining us on The Naked Scientist. Tell us about your work.
Well, I think the thing to get over here is that there are sort of three timescales where people try to predict weather in the future. There's the sort of daily weather forecast, what's going to happen tomorrow, or the next day maybe. Then there are these problems of climate change, where we might be talking about what's going to happen to the weather 100 years from now as a result of the emissions that we're putting into the atmosphere. We're changing atmospheric composition, which is changing weather. And then there's a third time scale, which is sort of lies in between the weather time scale and this kind of climate change time scale, which is what's going to happen maybe a few months into the future. And that's an area that I'm very much involved with a number of colleagues around the world. The key, in a sense, on this time scale of, let's say, a season or 2 seasons ahead, lies actually in the oceans. When we make a weather forecast for tomorrow, we assume that the ocean temperatures and ocean currents are pretty constant. They don't change from one day to the next very much. But on timescales of a few months ahead, then ocean temperatures and ocean currents really do change a lot. A classic example is the so-called El Niño phenomenon in the Pacific Ocean, where in the space of a few months, temperatures can warm by 5 or 6 degrees. And when this happens, it kind of throws the weather patterns around the world into complete turmoil. So by trying to predict how ocean temperatures and ocean currents evolve in the coming months, we can make useful predictions about weather on that timescale as well, so months to seasons ahead. And that's something that I'm very much involved in.
Now, when you come to draw up a model like this, how do you actually start? Because it's very easy to say, we're just going to make a few measurements and then work out what that does to the weather. How do you actually marshal that amount of information?
Well, essentially the problem is actually no different to that which Alex spoke about weather forecasting. So there are two essential ingredients. One is observations. And here the key is not just only observations of the atmosphere, but also observations of the oceans. So, for example, we have all sorts of different types of ocean measuring systems, buoys, and instruments which go down into the deep and then come up again and beam their information up to a satellite. So that gives us information about what both the atmosphere and the oceans are doing, let's say, right now. The second ingredient are these models that Alex spoke about. These are basically models based on the laws of physics, based on things like Newton's laws of motion, these sort of things which you learn about in school. These are the models which integrate forward in time the information from the atmosphere and from the oceans. The key difference between a weather forecast model and a kind of seasonal prediction model is that we need to represent not only the atmosphere but the oceans as well. So we have this kind of two-phase approach of getting both these complex systems into these computer models.
So we've had a question from Bob in Essex, and he says, OK, so you can predict the weather months in advance, but sometimes the weather forecasters don't even get it right next week. How do you look back on your predictions and work out how accurate you are and refine your models?
Yeah, I mean, that's a very good question, actually, because weather forecasts do go wrong. We've all seen that. And we have a scientific basis for understanding that, and it's a phenomenon called chaos theory. So things like the tides, for example, are very predictable. We can predict tides years, decades ahead. We can predict eclipses. We had an article earlier in this program about eclipses. We can predict eclipses, hundreds of years ahead. But these are not chaotic phenomena. The weather is a chaotic phenomena. Now, what it means is that we can never, when we go out to these timescales of months or seasons ahead, we can never make precise, absolute, definite predictions. What we make are what are generally called probabilistic predictions. So what we would do is say that, for example, the chance of it being wetter than normal or warmer than normal would be maybe 80% or 90%, depending on the confidence we have in the prediction. And this would be useful information because obviously all you can, without that information, all you would say is there's a 50% chance of it being warmer than normal or less colder than normal. So this is how we kind of deal with chaos theory in the weather by going towards a more probabilistic prediction. But nevertheless, in many applications, these turn out to be extremely useful types of forecasts.
Because it's often used by the climate lobby. Some people say, oh, well, weather forecasters, they can't tell it right. I mean, in a nutshell, what would you say to someone who said, oh, because you can't predict the weather next week, we don't know what global warming is going to do?
Well,
in a nutshell.
In a nutshell, we run the models, and what we make are probabilistic forecasts of climate change. So it is overwhelmingly likely that in 100 years it'll be warmer than it is now. Exactly how much warmer is actually hard to say. It could be anything between, say, about 2 degrees warmer and maybe up to about 12 degrees warmer. And that uncertainty reflects, to some extent, this chaotic nature of the atmosphere. Now, decision makers, have to take that into account. This is the best information the scientists can give them. There is a risk of I would say, quite catastrophic warming, but the most likely, based on these informations, the most likely warming is about maybe, 3 or 4 degrees above normal. But basically what we give to the policymakers are probability forecasts for the future.
And just to finish off, Tim, what about disease here? If we can tell what the weather's going to do, what impacts will that have potentially on our ability to handle and marshal diseases, which are obviously a major consideration with climate change or with weather in general?
That's right. I mean, there are many applications of these types of weather forecasts or these kind of seasonal type forecasts I've been speaking about. And one actually is in disease. Now, one of the biggest diseases in the world is malaria. This has been increasing over the years. Now, there is a type of malaria called epidemic malaria, which tends to occur in semi-arid regions of the world, where malaria is not the same, the incidence of malaria is not the same year in, year out. You get sudden pulses or years where there's a very strong incidence of malaria. And it's known this is related to weather variability. And in particular, years which are very wet tend to have these epidemics of malaria. So work that we've been doing in conjunction with scientists in the US is to make predictions of the coming rainy seasons, months ahead of time, whether it'll be above or below average. And by linking those to malaria prediction models, we can then give predictions of whether the malaria incidence in these particular epidemic-prone regions is likely to be above or below average. And then the authorities can target these areas months ahead of time. They're given effective warning to spray houses with insecticides, to provide children with bed nets, the sort of thing that really can save lives.
It sounds great, but is it actually working?
It is working. We are actually doing this now in the field. We published our results earlier this year based on a 20-year study of Botswana, which has very good malaria epidemiology. So we can test our prediction models and we can assess the skill and find out, in fact, there is very useful skill. And this is now being used in the field on a routine basis. So this is a very, I think, nice example of how we go from just weather forecasting, if you like, to something that really matters to a lot of, it's literally life and death to a lot of people in the world.
OK, Tim, thank you very much for joining us. Tim Palmer from the European Centre for Medium Range Weather Forecasts. Right, it's Chris and Kat as the Naked Scientists here. If you'd like to give us a call, 08459 25 2000 or email chris@nakedscientist.com. We're talking about the weather. Let me just ask a quick volley of emails, which you've had in quite a lot of these for you guys over there. This one's from Greg Wagner, and he's from Lubbock in Texas, and he says, I'm a PhD student in Texas Tech University, which is on the plains of West Texas. We're having a nasty dust storm, which brings me on to the question, what causes wind gusts, please, guys?
Friction, basically, in one word. You have a theoretical wind speed, which we call a geostrophic wind speed, and that's just the speed you would have if there was no friction. But when the air that's moving is in contact with the ground, then you get friction, and that takes a bit of the energy out, and it makes the bottom of the atmosphere very turbulent, and that's where you get the gusts from. It's this turbulence and this mixing in the bottom, sort of 2,000 or 3,000 feet, that causes gusts.
Got a question for you, Emily. This is Bernie in Peterborough. Says, how does the weather affect weaker ocean currents? Not strong ones like the Gulf, but other ocean currents.
How does weather affect weaker ocean...
Ocean currents, yeah.
Or is it the other way round? Is the ocean affecting the weather the other way around?
Well, I'm not sure. I mean, in terms of the ocean affecting the weather, then what we heard from Tim just a few minutes ago was that in terms of seasonal weather, then the ocean has a very strong influence. So if you're talking about doing weather predictions several months ahead, then you do very much need to look at the ocean temperatures. And in fact, if we look at this last winter, it's been incredibly dry here in the UK over the last winter, and that's been closely connected to the fact that we've had incredibly warm sea temperatures in the tropical Atlantic.
Why does that make a difference?
And so the incredibly warm sea temperatures we know we can look back to the summer, autumn, when, if you remember, there was large hurricane activity. We had the terrible hurricane in New Orleans. That was also connected with these warm sea surface temperatures. And for European winters, you basically have one of two situations. You either have a case where you have a very strong jet stream that brings all the storms across the Atlantic to the UK, and in those situations you typically will have warm, wet winters. Or you have another situation, which is where you have a much weaker jet stream and the storms tend to get deflected up north or down south. And in those situations, then you have typically a cold, dry winter in the UK. And whether or not you're in one situation or another situation is largely modulated by what the sea surface temperatures are like in the Atlantic Ocean.
So what can actually affect the temperature of the sea? And is it strong sunlight or motion? I mean, how does the sea change its temperature?
Well, the sea changes its temperature very slowly because water has a large heat capacity, and that's why these sea surface temperatures have this long timescale effect on the weather. So that's why sea surface temperatures tend to vary very slowly over the timescale of months, whereas we know the weather changes very quickly over days and hours even. And it's that slow change in the temperature of the ocean that causes the slow variability in the atmosphere.
I mean, we tend to think of, I tend to think of the sea as just a big homogeneous mass of water. But if you could see it and see the different temperatures and currents and saltiness, and what would our global oceans look like?
Oh, well, there are very different temperatures and salinities in different parts of the ocean. And in fact, the whole overturning circulation of the ocean,
the Gulf Stream, for want of a better word,
exactly, is driven by changes in density, which are due to changes in the salinity of the water and changes in the temperature of the water.
So adding a whole lot of fresh water from the North Pole because of melting of the Arctic ice sheets is actually quite a major issue then.
Certainly, in terms of the overturning circulation, in terms of the thermohaline circulation, then it would be an important issue.
Is there evidence that it's on the downturn? Because recent research suggests that actually it may have reduced by some 30 or 40%.
Well, there was some recent research that came out at the end of the last year suggesting that there was observational evidence that circulation had been slowing down. And indeed, if you do model predictions of the next 100 years or so, then you do predict a slow, gradual decrease in the speed of the overturning circulation.
And just very briefly, Emily, if that does occur, how much heat does that give to the UK, and what are the consequences for the UK's climate?
Well, that's quite difficult to say. I mean, I would like to stress that people might have seen the film Day After Tomorrow, but that film, the actual chances of the Gulf Stream completely shutting off...
I'd say 30% is a pretty big reduction, right?
Rather unlikely. But the Met Office has done a calculation where in an imaginary situation, they've tried shutting it off. And what they found was that for the UK, the temperature really was going to drop by 4 degrees or so. But I'd like to stress it's unlikely.
Laying the facts bare, the Naked Scientists.
We're talking this evening about the science of weather prediction and long-range weather forecasting and the changing global climate. If you'd like to join in the discussion, 08459 25 2000 or email chris@nakedscientist.com. Before then, we have to nip back to Downham Market School where Derek is out there with Sheena and our two volunteers, Matt and Sarah, to find out about the science of why the sky is blue. Derek.
Hi there, once again, welcome back to Downham Market High School, where we've got this experiment all ready to go, and Sheena's here ready with Matt and Sarah, who helped us set up the experiment earlier. So we've got the vase, we've got some water in there, we put a tiny bit of milk in there, so it's ever so slightly cloudy, and we've got a torch ready to shine through it. But of course, we do need to do this in the dark, so the teacher here at Downham Market is very kindly manning the lights. So, lights please. And here we go, we're in the dark now, so that's fantastic. All right, who's got the torch? Anyone got the torch?
Yes, I have.
OK, so I'm glad about that. OK, so hit the torch. And now what we need to do is for Matt and Sarah to shine some light through this vase and tell us what they see. So what direction would you like them to do first, Sheena?
So to begin, if they just shine the torch into the vase from one side.
OK, then. And now what can you see looking across?
Beam of light going across and the watery milk going blue where the light isn't.
Right, what's the next kind of condition we can try?
Now, if we shine the light from the same direction, but instead of looking at right angles to the beam, if we look straight in at the beam from the other side of the vase.
OK, so Sarah, this time, would you like to try that?
You can see through the glass. It looks the same.
OK, and Sheena, what's a good way to kind of see the effect that we're looking for here?
Yeah, it's nice. If you compare the colour of the torch beam when it's just shone onto paper, and then compare the colour when it's shone through the water and the milk onto paper, and just try comparing the colours of that.
OK, and we've got a bit of paper here, so if you shine the beam just onto paper, Sarah, what do you see?
Just a normal light.
And then if we shine it through the milky water, what then?
It goes a lot oranger.
All right, so Sheena, is that have we seen the right effect here?
Yep, what we've seen is the effect of when we see sunlight in the sky. Just to explain a little bit about light first, light is made up of all different colours, so you've got the whole spectrum, you've got from blue through to red. And then when the light shines onto the liquid, you've got little globules of milk. This is an emulsion. It's little globules of milk which are floating in the water. So this light comes in and it hits these globules of milk. But the different colours behave in different ways, and this is called scattering. And blue light is strongly scattered. So what you're seeing, when we saw that sort of blue haze, the blue light was scattered all over the vase. It was hitting these globules of milk, and the blue was sort of being scattered in all directions, and we could see this light sort of emitted from the whole of the vase of water.
OK, and just quickly, why is it that those different colours of light behave in different ways? Why does blue scatter?
It's a property of how much energy it's got. It's a different wavelength, so it's got a shorter wavelength compared to the red light, and it's also be an effect of how big the milk globules are.
OK, now where do we actually see this effect all around us?
So we see this effect every day when we're looking up into the sky. The sky is blue because the sunlight is shining down towards us, but as it's shining towards us, it's hitting all these different air molecules, and it's being scattered away. So when we see a blue sky, we're just seeing the blue light, which has been scattered in all directions, and then we sort of see it further away from the sun as it bounces into our eyes.
OK then, and so what about when we shone it through and saw that there was more of a red colour on the piece of paper when the torchlight was actually going through the milky water? What's going on there?
That's basically because we'd removed the blue light. So as I said, the light is made up of all these different colours. But when we remove the blue light, the white light no longer looks so white, and that's why we see the red, because the blue has actually been removed. If you find that you're not seeing the effect so well in your sort of like, if you've got a fairly small vase or something, if you do shine the light up from below, so it's travelling through more water, then a lot more of the blue light will be scattered. So then the light should appear much more red if you do it that way.
And so, of course, this reminds us of something that we see every day, which is...
the sun, basically. It's just the same as we see a yellow sun because some of the blue light has been removed and scattered round into the sky. And then also when the sun sets, it's at an angle to the Earth and it's coming through a lot more of the atmosphere, so much more of the blue is taken away, and that's why we see these lovely red sunsets. OK, so Matt, what do you think? Does that all make sense to you?
Yeah, it makes perfect sense.
Good stuff. And Sarah, I mean, you know, our mission here tonight was to convince you that science is actually great fun. I mean, how have we done?
You've done good. I think it's all right now.
Are you going to change your outlook completely?
Maybe a little bit.
OK, well, that's great. Well, thank you very much for doing this experiment with us, and thanks to Sheena for setting it up, of course, and to Downham Market High School for having us. We'll be back next week for more kitchen science, so hopefully you can do it at home. Until then, it's goodbye from us.
Thank you very much, Derek. Actually, I'm going to correct you there, Derek, because it's not next week, because next week we're off for Easter, and we're going to have a break here at The Naked Scientist. We won't be with you next week. We'll be back in 2 weeks' time, and Derek's going to be showing you how a submarine sinks to the ocean floor, and that's pertinent because on our next programme we're going to be exploring the ocean depths. But right now, we're still deep in conversation about the weather with Alex Hill and Emily Shuckborough here in the studio. Got a question for you guys. This one's from Anthony Claydon, who says, I listen to you on BBC Essex. The question is, on many different occasions I've noticed during a nighttime thunderstorm that the colour of the lightning can sometimes be pastel blue, sometimes yellow, or even green or pink. My question is, why does the colour of the lightning vary from one storm to another?
That's a $64,000 question, that one. That's a real cracker. It's probably, I mean, I'm not confident by this, but in any stretch of the imagination, it's probably actually to do with the amount of energy that's been discharged from the bottom of the cloud. Be slightly different, be going through different raindrops and these kind of things. But no, I really don't have a 100% answer to that.
Because the colour that you're seeing is going to be also dictated by the chemical behaviour of the things that get ionised or heated up by the lightning.
And what's between you and the lightning as well, you see.
Yeah, So if there's contamination in the atmosphere, perhaps that could play a role, couldn't it? Because street lights are orange because they contain sodium, and if you heat sodium up to a very high level, the wavelength of light it emits is an orange colour. So perhaps there are certain things in the air at that time that can affect the colour of the discharge.
That makes perfect sense, he says, hopefully.
How about grease lightning?
John Travolta. Right, another quick one here for you both. This is from Steve Cook, and he says, really enjoy your programme. We listen to it as we eat our Sunday roast in sunny Norfolk in the UK. I have a question for you. Sunny Norfolk, a bit dubious. On Tuesday morning, the BBC weather site forecast the next 5 days would be rain. On Tuesday afternoon, the same website had changed their forecast to be 5 days of cloud and sun. How can the forecast for 5 days change within a few hours? By the way, your website's very interesting. Thanks very much. And by the way, why do men have belly button fluff and women don't? You don't have to answer that, Alex.
No,
if you could very quickly, in 10 seconds, tell us,
It's all to do with chaos. It's what Tim was mentioning earlier, that the weather is chaotic, and so there are situations when it can be very unpredictable. So there's a 10-second answer. So there you go.
Thank you very much. Right, a big thank you to everyone for listening to us this evening and joining us here on The Naked Scientist. Have a wonderful Easter next week. We're away, having a damn nice holiday. Thank you very much to our production team, Anna Lacey, Petra Minch and Holly Barclay, and to our guests this evening. Thank you to Alex Hill from the Met Office, to Emily Shuckburgh from Cambridge University, and to Tim Palmer, who came in to talk about his weather predictions. Richard's our winner this week. Have a nice Easter.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.